So yesterday we have discussed up to this point interconversion from Fisher to Newman to Sahars to flying waves and all. So you should do practice here, then you will understand better way how to do. Okay, little bit we will see. Element of symmetry. Element of symmetry is very important to know about the molecular property when you are going to discuss about the enantiomer and diastereomer and all. That's why we will see little bit about this. You people have already studied in group theory and all, but little bit we will see here also element of symmetry. Because in enantiomers we are going to discuss. So if molecule is little bit complicated, it is very difficult to decide that is an enantiomer or diastereomer. So in enantiomer depends on whether a molecule is not superimposable on its mirror image. If it is superimposable, the molecule is optically inactive. Otherwise, it's optically active. The most convenient method of inspecting superimposability is to determine whether the molecule has any of the symmetry element. These are the some symmetry elements: plane of symmetry, center of symmetry, simple or proper axis of symmetry, and alternating or improper axis of symmetry. Plane of symmetry you can see when in tartaric acid, when meso compound is there, so there is plane of symmetry. Plane of symmetry means a plane which can divide molecule in equal to parts. That plane is imaginary plane. Okay, a plane of symmetry is defined as an imaginary plane which divides a molecule in such a way that one half is mirror image of other half. Then the molecule will be optically inactive. If that is mirror image of each other, means if one part is R configuration, other will be S. So they will cancel their optical activity by internal cancellation. So overall molecule will be optically inactive. So this is one example, very good example, mesotartaric acid. This is plane of symmetry, and this is this is mirror images of this image of this. This is optically. Now center of symmetry. The center of symmetry is defined as a point within the molecule such that if an atom is joined to it by a string, if extrapolated to an equal distance beyond it in opposite direction meets an equivalent atom. In other words, it is a point at which lines joining identities molecule. For example, here you can see here line. So both sides will get same atom. This side same atom. This side same atom. So any line, any side, you will draw a straight line, then after same distance, this side and this side, or this side and this side, you will get same atom. Then that is called center symmetry or inversion. This is an example: cis chiral and trans chiral, achiral. Cis is chiral, chiral. How? This is cis molecule. Okay. So this is the center point. If you will start from here, this side you will get CH3, this side you will get hydrogen. Rest of the side you will get exactly same atom, this and this and this. Only here and here you will get different atom. That's why this is chiral. But in this molecule trans, you will get same atom. both side. Here this side also, this side also, these. That's why this is achiral. Very good example. You should remember this. How this is achiral, how this is chiral. Simple or proper axis of symmetry, CN. What is CN? This is an imaginary line passing through the molecule in such a way that when the molecule is rotated about it by an angle of 360 by an arrangement is indistinguishable from the originally obtained. Such an axis is called n-fold axis of symmetry. For example, 1,3-dimethyl cyclobutane has two-fold axis of symmetry. This is one example, C2. Means here n is equal to 2. Cn, that n is here 360 by n. If n is equal to 2, then Cn will be C2, n is equal to 3, Cn will be C3, like that. So here, this is an example of cis-1,3-dimethyl cyclobutane. Cis, both CH3 group are same side, okay? That's why it is cis. This is that imaginary line. If you will rotate this, okay? So if you rotate from if you rotate 90-degree from here, then this will come exactly where this angle will be. Total is how much? This total angle is 360. So if you will rotate from here to here, it will come 90-degree. Then again you will rotate 90-degree. Then this will come exactly here. So this will be here, this methyl group will be here. So after rotation of 180-degree, you will get exactly same molecule. So what is axis of symmetry here? Axis of symmetry is 2, because 360 by 180 is equal to 2. So n is equal to 2. Then Cn is equal to C2. Now next one is alternating or improper axis of symmetry. Here two time rotation and reflection takes place. In previous example only we have rotated the molecule. Not any reflection is there. But this is combination of both. This is one example. 1, 2, 3, 4 tetramethyl cyclobutane. So CS3 group is here. This cis and 3, 1, 3 is also cis with respect to each other. But 2, 3 is trans, 3, 4 is trans, like that. Okay, alternate up and down. So if you will rotate by 90-degree, 90-degree, then this will come, this carbon will come here, this will here, this will here, this will here. Means just one will take place the position of 2, 2 will be of 3, 3 will be of 4, 4 will be at place of 1. This molecule you will get after rotation by 90-degree. Now if you will make a mirror, you will put a mirror plane here, then what you will get? You can see mirror plane. So this will be like this carbon will be like this, okay? And this will be here, and this will be here. Now these two are superimposable. So after rotation and reflection, you will get indistinguishable molecule. So it is called alternating or improper axis of symmetry. It is denoted by SN. Okay. So here n is equal to again 360 by angle of rotation. So angle of rotation is equal to 360 by 90. So that is equal to 4. So Sn is equal to 4 in this case. Now we will see asymmetry and asymmetry. In general, the asymmetry is used for those applicative compounds which have none of the four elements of symmetry. In contrast, the term disymmetry is used for all stereoisomeric compounds which are capable of existing as pair of non-superimposable mirroring. It means disymmetry molecule will be asymmetric, but all asymmetric molecules are not necessarily having disymmetry. Disymmetry molecule will be always optically active. In other words, the disymmetry is applicable for all stereoisomers which are related to each other as non-superimposable mirror image of each other. It means they are optically active, always optically active. This is one example. Structures of these two and three, you can see here this molecule first. Rotation by 180. If you rotated 180-degree, okay, so what you will get? This will be here, this will be here. Where you have rotated. This is constant, it means you are rotating. Oh, this is the vertical axis. So you are rotating in such a way that CS3 is coming here. This CS3 is going here. Okay. And rest of the molecule, how is it going on? Again, this will come here and this will come here and this will come here. This hydrogen will come here, means indistinguishable. And mirror image of this one is this one. And after 180 rotation, you are getting this one. So this here in this case, C2 axis of symmetry is there. By rotation of 180 degree, you are getting is indistinguishable molecule. So this is C2 axis of symmetry, but it is not superimposable on its mirror image. So it is disymmetry and not asymmetry and exhibits optically. It means not only rotation, reflection, and all, it's superimposability you have to check. Okay. All asymmetric molecules are disymmetric, but all disymmetric molecules are not asymmetric. This is mentioned here. Means every molecule which will be optically active will be disymmetric. Okay. However, both these types of molecules show optically activity and have chirality. That's why now many places it is written as asymmetry or disymmetry. The term chirality is used. Now stereogenic center or chiral center. Tetrahedral carbon atom bearing four different atoms or groups may be called as chiral center, symmetric center, asymmetric carbon, chiral center, stereogenic center, and stereo center are of enantiomers. Now, what is enantiomers? We have already discussed. Okay, so now characteristics of enantiomer. Molecule should be chiral or disymmetric. 3 to 4 will. Okay, sir. That's 5 I have on online today. Last till 7. Which interview? For selecting project students at University of Kolkata. Okay, okay. Okay, sir. So, so its mirror image should be non-superimposable. This is always it is there with active molecule. This statement is a kind of universal truth. Having more than one chiral center, they will show an enantiomerism and they will be optically active. But if the molecule having more than one chiral center, but there is mirror plane of symmetry, then that is optically inactive because internal compensation takes place. What is internal compensation? Both chiral center will cancel the activity of others chiral center. Compounds having chirality in this type of molecule where there is no asymmetric carbon. Means these molecules show chirality or disymmetry, and hence in enantiomerism, these are orthosubstituted biphenyls and allenes are the good example. So this is also called atropoisomerism. This term is not used here. हेलो, ये यही टाइम कॉल करती हैं. Atropoisomerism. This is rotation is hindered here. Means molecule cannot rotate. If molecule will rotate in this case, then they can come to this side and there will be mirror plane here. But molecule rotation is hindered in these cases. That's why there will be asymmetry, non-superimposable mirror images. You can see here in this example, this is mirror image of this one. So these two are non-superimposable. If this is rotation is possible, then they can get. But there is no chiral carbon. You cannot get any chiral carbon. This carbon, this carbon, and not a single carbon which is chiral carbon. Okay. So another is that is allene. Allene means continuous double bond is here due to the sp hybridization of central carbon from two pi bonds perpendicular to each other, and thus the two groups attached to terminal carbon atom are orthogonal. Due to this arrangement, the molecule of allene is devoid of symmetry and hence is chiral. Again, just like previous example, this is also allene is also like that. So you will get here. This is mirror image. Mirror image is not superimposable of each other. If you will put it this one here, if you will rotate this molecule, you want to bring like this, then this will be different than this. So you will not exactly get uh, superimposability in this molecule with its mirror image. So therefore, necessary and sufficient condition to exhibit enantiomer is that they should possess chirality or disymmetry rather than asymmetry. Now, properties of identical physical and chemical properties differ in the direction of rotation obtained polarized light. We are knowing specific rotation, you can see plus and minus. Tartaric acid plus and tartaric acid minus. You can see what is the difference here. Melting point is same, solubility is same, insolubility is same, density is same. Only what is the difference is specific rotation is just opposite to each other. Mesotartaric acid also having many differences. Melting point will be totally different, solubility will be different, density will be different. So you can easily differentiate meso compound with the any enantiomer. Racemic mixture means equal amount of both enantiomer, then rotation will be zero. The enantiomer have identical chemical property towards optically inactive reagents. Means reaction will be same if there is optically inactive reactant is there. For example, you can see here Plus and minus, both molecule will react with HBr and this will give plus and minus, same kind of product. H2SO4, same. CH3COS, same kind of reaction it will give, same kind of product. But with optically active reagents, what is the response? Response will be different. If we do reaction of two enantiomers, for example, lactic acid plus and minus, then the reagent will not be identical with both due to the different spatial disposition of the different group in the two enantiomer in relation to the group attached to the chiral center. Therefore, the rate of esterification of 2-methyl-1-butanol will be different from that of minus 2-methyl-butanol. Means both plus and minus, these have different reactivity with optically active reagents. So if you want to differentiate them, then you can do reaction with the optically active reagents. The enantiomer have different biological property. Both enantiomer have different property due to their stereoisomeric arrangement. For example, plus glucose play important role in animal metabolism and fermentation, but minus glucose is not metabolized by animals and furthermore cannot be fermented by yeast. Very important point. You should remember this. Penicillium glaucum consumes only the plus enantiomer when fed with the mixture of equal quantities of plus and minus tartaric acid. Hormonal activity of minus adrenaline is many times more than that of its enantiomer. Now we can see if molecule has several chirality centers, then what is the meaning of this? If there are more than one chiral carbons, means n is equal to any number, more than one. The compound will exist as 2 to power n optically active forms, provided chiral carbons are not identical, substituted. Means all groups are different, then that is equal to 2 to power n. 2 to power n. For example, 2 bromo 3 hydroxybutane diuric acid. Two chiral carbons are there. So number of existing isomer will be 2 to power 2 equal to 4 active forms. Sometimes if groups are similar, then this number will be less than that. But this is the maximum number of possible isomers. This is one. This is that example of tartaric acid. 1 and 2, 3 and 4. 1 and 2 is a pair of enantiomer. 3 and 4 is a pair of enantiomer. You can see these two are same. What is the relationship between 1 and 3? And what is the relation between 1 and 4? All are optically active, but are not the mirror images. Okay. Such stereoisomers are referred to as diastereomers. Means first and second is enantiomer, but first, third, first, fourth, these are diastereomer. Okay, it's in the same way. Second is enantiomer of 1, but diastereomer of 3 and 4. Enantiomer, mirror image, diastereomer, there is no relation or impossibility. Properties of diastereomer, you can see how they are different. Diastereomers, you can see here what is the difference. Optical activity may be anything, plus and minus. Okay, melting point will be same, solubility will be same, relative density will be same. So therefore can be easily separated using techniques such as fractional crystallization. Fractional distillation relation. Okay, and chromatography. Okay, different behaviors towards plain polarized light. To maybe enantiomer, okay, this and this, these two diastereomer relation. So you can see totally different property. Diastereomer has similar but non-identical chemical property. Particular, they react with chiral or chiral agents at different rates. So reaction will be also different. Now 3,183 diastereoisomer. What is 3,183 isomer? You can see in this example, throws minus, it throws plus, minus 3 O's and plus 3 O's. What is common here? Molecular formula is same. Only difference is that in erythros, OH groups are same side cis with respect to each other. In this, OH are trans to each other. So this is triose structure. This is the erythriose structure. Okay. So in Fischer projection, give the impression that the molecule exists in the eclipsed form. Therefore, it exists in the staggered form, in which the bulky substrates are as far apart as possible. Therefore, an stereoisomer corresponds to that diastereomer. The chiral carbons has a rotational isomer in which all similar groups are eclipsed. Means if you will see from here to here, this it is not like that. So erythrios will give eclipsed with similar groups, but trios will give different groups eclipsed. Okay, major compounds enough you are knowing here. No problem. These compounds we discussed many times. Number of isomers we can calculate here. Number of optical isomers to the power n. Number of mesoforms. It depends on the molecule having dissimilar chiral center or similar chiral center. If they are not similar, mesoforms will be zero. If they are similar, then there will be some mesoform. Okay. If molecule having even number of chiral center, this will be to the power n minus 1. If no, and then number of mesoforms will be to the power n by 2 minus 1. These are some formulas to calculate the number of optical isomers. Number of optical isomer is 2 power n minus 1 minus 2 to power n minus 1 by 2 if number of chiral center is odd. Here it is for even, and number of mesoform is equal to simply 2 to power n minus 1 by 2. So these are some formula related to chiral centers and number of isomers, stereoisomers, optical isomers. You can see another example. This is 1, 2, 3 triol. So 1, 2, 3, 4 molecules here it is drawn. Two similar chiral carbons are there. Okay. So second and third, not first and last carbon. So in this case also total number of stereoimer is 4 to 2 power 2. Tartaric acid also number of optical isomers 2 to power n minus 1 because both are similar and it is even in number. Mesoforms is also you can calculate and total number of stereomers also you can calculate. There is no issue in this. In the same way here you can calculate, but here this is number of chiral center is odd. Previous one it was even, here it is 3 carbons are here. So formula will be used. This one different, not previous one. Now one term is a prochirality. Many times in textbook when you are reading there is one term is prochirality. Prochiral means pro. Many times you have heard that he is pro regarding means if you are belonging to any party, then people will say that he's pro this party, pro that party, like that. So in the same way here, pro chirality means it is very much close to chirality. Only one small trigger it will give a chiral. Gives an such a hydrogen atom is called enantiotopic hydrogen. And that enantiotopic hydrogen, the replacement of which gives configurational isomer. If it will give R configuration, then starting material will be pro R. If it will give S, carbon atom to which the two hydrogen atom are attached called prochirality center, and the molecule is called prochiral molecule. Okay. For example, in this molecule, two hydrogens are there. If one hydrogen will be replaced, it will give chiral. This will be replaced, also it will be chiral. But if this will be replaced, it will give S isomer. If this will be replaced, then it will give R isomer. So this hydrogen is called pro S. This will be called pro I. Retention or inversion of configuration. This is we have discussed in few days back. In SN2 there is inversion. In SN1 there is retention and inversion. Both takes place. Equal chances are there. Racemic modification or racemic mixture. What is this? An equimolar mixture of two enantiomer does not have optical activity and is called racemic mixture or racemic modification or conglomerate. Any term people can use. So meaning is same. Equimolar enantiomeric mixture. Cancellation of one enantiomer by another enantiomer. So this is called external compensation. In isomer, there is rotation, optical activity is cancelled by within the molecule compensation. But in this case, it is external compensation. These are the difference. And some prefixes such as small dl or plus or minus or rs are used before the name of compound to specify that it is racemic or pure. Then optical rotation as well as other physical property are mixture, melting point, boiling point, solubility in a given solvent, etc. are also different from those of enantiomers. Racemic mixture have optical activity 0. How to do racemization? Some methods are there. Racemization is involving a carbon ion as an intermediate. Racemization involves a carbocation as an intermediate. Racemization involving Walden inversion. Racemization involves rotation about carbon-carbon single bond. These are the different methods. You can see here minus lactic acid plus lactic acid. Okay, so this can convert this way. We are not going to discuss because in your syllabus these terms are not in detail. So only I'm giving a brief idea about it. You are knowing here this is SN2 reaction. This is racemic mixture. Racemization involves rotation of CC bond as we discussed. Method of resolution. Many methods are there. Mechanical separation, preferential crystallization, biochemical method, resolution, chromatographic method. This is very important for competitive exams. Many times it is asked that how to separate in an enantiomer. What is the method of resolution? Then you should know mechanical method. What is that? So how you can do? Means if racemic mixture is there, then both types of enantiomers are there. So it can be separated by usually This here one example is given about the visors and magnifying glasses. That's why it is called mechanical separation. If there is no reaction, only due to their different size, different orientation of the substrates or groups, it can be. And crystallization method is the best method. You can preferentially crystallize a closed any enantiomer, and you can easily crystallize any enantiomer as in a co-crystal form. Okay, so if you want to crystallize R, means here supersaturated solution of receiving mixture is inoculated with a crystal of one of the enantiomer or an isomorphous crystal of the another chiral compound. For example, if plus minus sodium ammonium tartrate is seeded with a crystal of one of the pure enantiomer in a crystal minus or plus, okay, then if minus you will add, minus will crystallize first. If plus you will add in that solution, plus will crystallize first. So here, one a kind of seed is added within the solution. That seed is, if you are adding minus, you will get minus. If you are adding plus, you will get plus in enantiomer. And here this seed crystal is called entrainer, and this method is called entrainment. Microorganisms are also used to separate. For example, fermentation of plus minus tartaric acid in presence of yeast, only plus tartaric acid will be consumed, leaved behind minus tartaric acid. Hello? हाँ. अच्छा. अच्छा अच्छा. अच्छा अच्छा. अच्छा अच्छा. अच्छा. हम्म. अच्छा. हाँ. अच्छा अच्छा. पता नहीं 2 सप्ताह हो गया इसलिए मुझे शक हुआ. हाँ हाँ, बहुत पॉसिबिलिटी है. कोरोना का भी डर है एक्चुअली. हाँ हाँ. हम्म. हम्म. चलिए ठीक है. ठीक है. ओके. So, but here there is also some limitation in all these methods. This can be done in dilute solution, so isolation of product becomes very difficult. This is I'm just giving a brief idea because this will not come in your exam. There it is not in your syllabus only, but you should know for competitive exams it is very important. They can ask how to separate in enantiomer, how to, if residue mixture is there, then what are the methods. So you should know little bit about this. For example, here you can see here. So racemic modification, how we resolving agent is this one. If minus syncholine will be added in tartaric acid, then you will get minus with this and separated as a crystal, minus with minus, and plus and minus will be like this, plus tartaric acid, and minus crystallize out. This will not crystallize out. When we will add dilute testosterone, then this will crystallize out. So these two can be separated very easily by using diisomers, separable diastereomers. So this is the best method. It is applied separation of racemic mixture in enantiomers from racemic mixture. So some advantages are there. I will give you this. You can read it. Chromatography method is also there, but it is not very easy. In this method also, to an enantiomer, it is very difficult to separate. But solvent, some good solvent should be used and column length should be good. And convert into diastereomers, then only it is separated. Otherwise, it is very difficult. Diastereo, this that is a complex. Means it will make a complex with one enantiomer will be added, and that will make a it will combine with that one, and two combine and minus will also combine with that molecule, but their mobility and all will be different. So elution time will be different, and you can separate by chromatography method. Now absolute and relative configuration. What is this? Absolute configuration groups in this space. In the space, we will start from here again from in class, but again today few minutes are left, so I will give a brief idea here again. So absolute arrangement is the atoms are groups of atoms in the space of a particular stereoisomer of a compound. It can be studied through crystal X-ray or of pure compound. Relative configuration, the right relative arrangement of, for example, here configuration A is was arbitrarily assigned to designate configuration of plus glyceraldehyde. A is plus glyceraldehyde. This is arbitrarily assigned. Is on left. Taking this as a standard, the relative configuration of minus lactic acid is assigned as this one. Hmm. You people are, I know. So glyceraldehyde plus and glyceraldehyde minus. If one is standard, then another will be decided based on that. So if A is standard and this glyceric acid is minus is there, so it is represented, it can be discussed in terms of glyceraldehyde orientation of OH group. So that is relative. But if there is no relative molecule, only we are going to discuss the property of glyceraldehyde without any relative molecule, then that will be the absolute configuration. Again, we will discuss tomorrow. Okay, I think class is over today. Again, same time we will start tomorrow from here. Absolute and relative configuration.